Measuring enthalpy changes, calorimetry. An important property of reactions is that they can release or absorb heat. We will learn how to measure the heat produced or absorbed by reactions that occur in solution in a process called calorimetry. We will make use of the fact that the energy flow as heat from a reaction is a measure of the enthalpy change of the system. Couple definitions. The amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius, because they're the same size units, is heat capacity. It is an extensive property in that it depends on the amount of the substance. Then we have specific heat capacity, represented by a lowercase c, which will be joules per gram Kelvin or joules per gram degree Celsius. That's the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius. It is an intensive property in that it does not depend on the amount of substance. It is often just called specific heat. Specific heat capacity is the heat transferred, or Q, divided by the mass times the temperature change. Here it is in equation format, Q over m delta T. We solve that for Q and we get Q is mc delta T. The units of C are either joules per gram Kelvin or joules per gram Celsius. And specific heat capacity has the same value in Kelvin or degree Celsius because the size of those units is the same. When a reaction occurs in an isolated aqueous solution, as shown here, okay, we have water, and then we have a styrofoam cup, and we're measuring a change in temperature with a thermometer there. The water acts as the surroundings, and the reactant chemicals are the system. The reaction changes the chemical potential energy of the reactants, the system. That results in an equal and opposite change in the thermal energy of the system due to conservation of energy. That change in the thermal energy of the system results in a change to its temperature. The system and the surrounding water are now at different temperatures. Heat will flow from the reactants to the surrounding water until their temperatures are equal. The temperature change of the combined water and reactants is measured by a thermometer. The change in the thermal energy of the water and reactants is found by using the specific heat capacity of water. That change in the thermal energy of the reactants in water, measured by the thermometer here, is equal and opposite to the change in chemical potential energy due to the reaction. Thus, the heat of the reaction is indirectly measured by the change of temperature in a simple calculation. Assume that the reactants have the same specific heat as water. That's a reasonable approximation given the relative amounts of each. There's way more water than reactants.
Example 1, calorimetry. A student determines the heat of solution for ammonium chloride, NH4Cl, which is the enthalpy change when NH4Cl dissolves in water by measuring out 20 grams of ammonium chloride and adding it to 500 grams of water in a styrofoam cup. The initial temperature is 16.1 degrees Celsius, and the temperature decreases to 13.2 degrees Celsius. What is the enthalpy change for the dissolution of ammonium chloride? Noting that the masses of water and ammonium chloride were summed. So we have the mass of ammonium chloride, NH4Cl, as 20 grams. The mass of the water is 500 grams. So the total mass in the calorimeter in the styrofoam cup is 520 grams. Then we're also told that the initial temperature is 16.1 degrees Celsius, and the final temperature is 13.2 degrees Celsius. Okay, so if the temperature is decreasing, I want you to try to make a prediction. Do you think this is endothermic? Do you think this is exothermic? Will we get a heat of solution or an enthalpy change that is greater or less than 0? Something to think about. Let's take a look at how we work this out on the next slide. All right, so the first thing we're going to do is find the enthalpy change in the surroundings. And I've bolded it there. I'm also going to highlight it. Remember that the thermometer is measuring the surroundings. Okay, so that decrease in temperature is a decrease in temperature to the surroundings. So the change in enthalpy, or Q, is equal to the mass, which we talked about on the previous slide, is that total mass, times C, 4.184 joules per gram degree Celsius, times delta T, which was a decrease in temperature of 2.9 degrees. And then we get a delta H of minus 6,310 joules. All right, so this is why back 2 slides ago I asked you to kind of think about this, because the thermal energy of the surroundings and the system decreased, so the chemical potential energy of the reaction must increase by an equal amount to conserve energy. So the delta H for dissolving ammonium chloride is positive 6,310 joules. So of note, this is an endothermic reaction since heat from the surroundings flows into the system. And that heat flowing into the system is measured by that decrease in temperature in the surroundings in this case.
Often, when doing calorimetry work, we want to calculate an enthalpy change per gram or per mole of substance dissolving, reacting, or precipitating. To do this, divide the enthalpy change of the system in joules by the amount of reactants. This reaction, which is combusting hydrogen with oxygen, proceeds with 2 moles of hydrogen reacting with 1 mole of oxygen. Right? 2 moles and then a 1 mole here. The enthalpy change is minus 572 kilojoules. What is the enthalpy change per mole of hydrogen? What is the enthalpy change per mole of oxygen? We're given the change in enthalpy, and the equation tells us we have 2 moles of hydrogen and 1 mole of oxygen. So it's a matter of just dividing the enthalpy by the amount of moles. So for hydrogen, we divide by 2, and we get minus 286 kilojoules per mole of hydrogen. And for oxygen, we divide through by 1, and we get minus 572 kilojoules per mole of oxygen. This reaction proceeds with 50 milliliters of 1 mole of hydrochloric acid reacting with a 50 milliliters of 1 mole of sodium hydroxide. The enthalpy change is minus 2,890 joules. What is that enthalpy change per mole of sodium hydroxide and per mole of hydrochloric acid? First, find out how many moles of sodium hydroxide are reacting. Well, molarity is equal to moles per liter. So molarity times liter tells you how many moles you have. We have 1 molar hydrochloric acid and we have 0.050 liters of it. So that gives us 0.05 moles of hydrochloric acid, and look at the coefficients here. Both of them have 1. So if 1 mole of hydrochloric acid reacts, then you have 1 mole of sodium hydroxide. In this case, we have 0.05 moles of hydrochloric acid, so that reacts with 0.05 moles of sodium hydroxide. So the enthalpy change in joules per mole will be the enthalpy change here. Divide that by how many moles of sodium hydroxide, and we get minus 57,800 joules per mole, or minus 57.8 kilojoules per mole. Since there are an equal number of moles of hydrochloric acid, the enthalpy change per mole of hydrochloric acid will be the same, negative 57.8 kilojoules per mole. Reactions can be carried out in a sealed bomb calorimeter, such as this one, in order to prevent any change in volume. The heat absorbed or released by the water in the calorimeter is a very good approximation of the magnitude of the enthalpy change for the reaction. So you can see here's our enclosed container here. Thermometer goes through a narrow hole. We have something here to stir things up, and we have ignition wires here to burn stuff. Because the volume in the bomb calorimeter is constant, no work, which is P delta V, is done. Okay, there's no change in volume. And what is measured is really the change in internal energy, delta E, not delta H. But for most reactions, the difference is very small. So we have delta E equals QV, where QV is the heat capacity of the calorimeter times delta T. QV is C delta T. Heat capacity has units of joules per Kelvin or joules per degree Celsius. And here's our definition of what's going on here. The heat capacity of the calorimeter is the energy required to raise the water and parts of the calorimeter by 1 degree Celsius or 1 Kelvin. A student wants to find the heat capacity of a bomb calorimeter, constant volume, by burning 1 gram of ethanol. The temperature of the water rises from 18.7 degrees Celsius to 55.4 degrees Celsius as 26,800 joules of heat are released. Calculate the heat capacity for the calorimeter. We have our givens, the mass of the ethanol, initial, final temperatures, and Q sub V. Here's our heat capacity equation. We solve that for C and find that's QV over T. We substitute in our givens and we get C is equal to 730 joules per degree Celsius. Please note the enthalpy for the system was put in as a positive value even though it was an exothermic process. This was done so that the heat capacity has a positive value. The heat capacity of a bomb calorimeter is always expressed as a positive value. A student uses a bomb calorimeter, constant volume, with a heat capacity of C equals 730 joules per coulomb to determine the heat flow when 0.50 grams of sodium reacts with water. The temperature of the water rises from 20.2 degrees Celsius to 25.7 degrees Celsius. Calculate the heat flow. Our givens, right? Heat capacity, mass, initial, and final temperature. We have our heat capacity equation. We just go ahead and substitute in our values, and we get a Q sub V of 4,020 joules.